Hey there, AP Chem fans. Today we're going to be talking about AP topic 9.7 in electrochemistry, galvanic, also called voltaic cells. So just a reminder, electrochemical reactions, also called redox reactions, are reactions in which one element gains electrons and one element loses electrons. In this particular reaction, you'll notice that we have zinc reacting with hydrogen ions to produce zinc ions and hydrogen. In this reaction, zinc is losing electrons. You'll notice its oxidation number goes from 0 to positive 2, and hydrogen is gaining electrons. It's going from a 1 positive to a 0 charge. And so whenever you have a redox reaction, you're always going to have a loss of electrons and a gain of electrons. So oil rig is a way that you could remember this. Oil oxidation is loss of electrons. So zinc goes from 0 to 2 positive, so it lost 2 electrons, and that means it was oxidized. Rig in oil rig is reduction is gain of electrons. So if you'll notice, hydrogen has a 1 positive charge, and it goes to a 0 charge. Now notice there are 2 hydrogen ions. Each one gains 1 electron, and so each hydrogen ion is reduced from a 1 positive charge to a 0 charge. And this idea that in a redox reaction, one element loses electron, one element gains, always has to go together. You cannot have an element lose electrons and those electrons go nowhere. They have to be gained by something. And so redox reactions always occur in pairs. And most of the time, we write these in half reactions where we show the reduction happening and we show the oxidation happening. So here's an example of 2 half reactions. If you put a piece of zinc metal into a solution of copper sulfate, you will see a reaction happen spontaneously. What happens is the zinc ions will lose 2 electrons and go into solution to form zinc ions. And so in this diagram down here at the bottom, you will notice that the zinc atoms are in metal 4 metallic form. They lose 2 electrons to the copper ions that are floating around in the solution. So the zinc ions come out of the metal and now are ions floating in solution. The copper atom, which gained 2 electrons, will now just attach itself to the surface of the zinc as a neutral copper atom. And so the 2 half reactions are written over here on the right. You'll notice that we have zinc producing zinc 2 positive ions and then 2 electrons. Those 2 electrons are then absorbed by the copper 2 positive ions to produce copper metal. And then if we add the 2 reactions together, we get zinc metal plus copper 2 positive ions produce zinc 2 positive ions plus copper metal. We can use this type of reaction to do work for us. If we can make the electrons that are transferred in this reaction flow through a wire, and then we attach some electrical device to that wire, the electrons in their transfer from one reaction to another can be used to do useful work for us. And this device that allows us to do this is called a galvanic cell. Sometimes we call this a voltaic cell. And again, this separates the 2 half reactions using a wire to allow for the transfer of the electrons from one of the half reactions to the other half reactions. And then we can use that wire to power those electron transfers to power whatever it is we're looking to power. So here's the basic setup for a galvanic cell. And it looks a little overwhelming, but we're going to go through each part. So first off, one side of the cell has both atoms, a piece of metal, and ions, a solution of a salt containing the ions of the metal, of an element that will be reduced. So on the left beaker here, you will notice that we have a solution that has zinc ions and nitrate ions. So zinc nitrate was dissolved in water. And then we have a piece of zinc that is put into that solution. So we have both zinc atoms present in the metal and zinc ions present in the solution. On the other side of the reaction, in a separate beaker, we have both atoms and ions of the element that's going to be oxidized. In this case, copper. So we have a copper nitrate solution where copper ions are present on the right-hand side in the solution. And then we put into the solution a piece of copper metal. And so the zinc metal and zinc ions are in one side of this galvanic cell. and copper metal and copper ions are on the other side of this cell, and they're kept separate from one another. However, they are connected by using a wire that connects the metal on the oxidation side and the metal on the reduction side. When we connect these two, this allows a path for electrons to transfer from one half reaction to the other half reaction. The pieces of metal are called electrodes, and electrodes are simply metals that act as surfaces where electrons can transfer. On the oxidation half reaction, the electrode is called the anode, and on the reduction side, the electrode is called the cathode. One way you can remember that the anode is on the oxidation side and the cathode's on the reduction side is red cat and ox. Reduction occurs at the cathode, and the anode has oxidation. So red cat and ox. So like I said, the electrons are produced at the oxidation half reaction. So if you look at the oxidation side of this reaction, electrons are transferred from zinc, making zinc ions. Those two electrons then travel upwards through a wire over to the other half reaction. And at the other half reaction, we have a surface now where the ions in the solution, copper 2 positive, can absorb those two electrons and attach themselves to the cathode, becoming copper atoms. So they go from copper ions to copper atoms. So zinc loses 2 electrons. The electrons transfer through the wire to the other electrode called cathode. Those electrons then can attach to the copper 2 ions in the solution, and the copper 2 ions are now copper atoms. So the two half reactions occur. Zinc atoms lose 2 electrons to become zinc ions, and copper ions gain the 2 electrons to become copper metal. While the electrons are traveling through that wire, we could hook up a light bulb or any other device that we wanted to power, and the electrons would power that device before they go to the copper ions to become copper metal. As positive ions leave the anode, the solution becomes more positive because the zinc ions are going into the solution. And the same is true on the other side. As copper ions leave the solution becomes more negative. That cannot be. You cannot have unbalanced charge in these two half solutions. And so what happens is we have to balance the charge somehow. The way we balance this charge is by using what's called a salt bridge. This is something that will complete the circuit. And if you've taken physics, you know that electrons won't flow through a circuit unless the circuit is complete. And so a salt bridge completes the circuit. What a salt bridge is a tube, usually U-shaped tube made out of glass, that has salt in it, usually sodium nitrate or some other completely soluble salt. And as zinc ions go into solution, as positive ions go into the solution, that positive charge is balanced out by negative nitrate ions flowing into that solution. And for every zinc ion that is produced, 2 nitrate ions will flow into the solution to balance the charge. And the same is true on the other side. As copper 2 positive ions leave the solution and become neutral copper atoms, positive sodium ions will replace those positive ions that left. And for every copper 2 positive that leaves, 2 sodium ions will flow into the solution to balance the charge of the nitrates that are left behind. So a salt bridge simply completes the circuit and balances the charge of the ions that have left or are being put into the solutions in the two half reactions. Without the salt bridge, this reaction would not occur. Electrons would not be able to flow because there would be an unbalance of charge in the system. Electrons will only flow one way in a redox reaction. They always flow from higher electrical potential overall to lower electrical potential. And one way to think of this is an analogy with water. If you have water high up, it'll always fall from a high potential energy to a low potential energy. And this is what causes waterfalls. Waterfalls never flow upward from low potential to high potential. We can lift water up, but we have to put energy in to lift water up to a higher place. But water will always spontaneously flow in one direction, from high potential energy to low potential energy. Electrons are the same way. Electrons will always flow from higher potential to a lower potential based on the half reactions in an overall reaction. What causes this is what's called electromotive force or voltage. Voltage is the force behind the electrons in a reaction. And we call this potential difference the electromotive force. It's the potential energy difference between two half reactions. We designate the electromotive force in a cell as E cell. And cell potential is measured in volts. And again, you can think of volts as the push of charge. Amps are the flow of charge. And so voltage pushes electrons through a circuit. Voltage is 1 joule per coulomb. A joule is a unit of energy. A coulomb is a unit of charge. So it's how much energy does it take per unit of charge to in a galvanic cell. So again, think of cell potential or voltage as the push of electrons. So here is a table of the standard reduction potentials for a whole bunch of different half reactions. Again, some reactions will happen very spontaneously and some reactions will not happen spontaneously. In other words, some substances will gain electrons spontaneously because that lowers their electropotential. Some substances will not gain electrons very easily. So in this chart, up at the top, you'll notice that we have fluorine. Fluorine gas gains electrons extremely easily, and so it has a high positive potential energy, a high positive voltage. So fluorine will gain electrons easily. It'll be reduced easily. As we go down the chart, you can see substances that are reduced less and less easily. Eventually, we get down to zero. Zero is hydrogen, and this is our standard reference electrode. Hydrogen is used as a reference for all the other substances. So in order to determine the voltages of all the other substances, they're reacted with hydrogen ions, and the voltage is measured for that reaction. So all of these voltages come from what's called a standard hydrogen electrode, where hydrogen is defined as 0, and then all the other potentials are relative to the hydrogen electrode itself. You'll notice that there are some substances below hydrogen on this table that have negative voltages. And that means that these are non-spontaneous half reactions. They do not happen spontaneously on their own because they don't gain electrons spontaneously. They could occur if they are paired with another half reaction that has a very high potential, a very high voltage. And we'll talk a little bit more about that in a couple of minutes. So again, positive reduction potentials indicate that the process is thermodynamically favorable. Negative reduction potentials indicate that the process is not thermodynamically favorable. If we reverse any of these half reactions and make them run the opposite direction, then that would be oxidation. And so if you look at the very bottom of the chart, you'll see lithium ions do not gain electrons spontaneously. In fact, it's a very negative voltage. They really do not like to gain electrons. But if we flip the reaction and write it as lithium metal losing an electron to become lithium ions, then what happens is the voltage will exactly flip. It will now be a positive 3.05 volts because lithium metal very easily spontaneously loses an electron. And so when we flip all of these reduction half reactions to make them oxidation half reactions, we simply flip the signs of all the potential energies, and that allows us to figure out what the oxidation potential is for any reaction. So notice that if we had fluorine, the element, reacting with lithium, the element, that would be an extremely spontaneous reaction because fluorine loves to gain electrons and lithium loves to give electrons. And so this reaction would be a very spontaneous reaction. And we'll learn a little bit more about that in a second. So I already talked about the standard hydrogen electrode, so I'm going to skip this. So standard cell potentials, the way that we can calculate the energy of an overall galvanic cell is by adding the reduction voltage and the oxidation voltage or cell potential. If we add those two together, we will get the cell potential for the overall reaction. So I've got a simplified reduction half reaction table over on the right here, and we're going to calculate the cell potential for this reaction, where zinc plus copper ions produces zinc ions plus copper. This is the reaction we saw at the beginning of this presentation. So copper is reduced. Copper 2 plus is reduced. So we can just look on this table and we'll notice copper 2 positive plus 2 electrons makes copper, and it's 0.34. So 0.34 volts is the voltage for this half reaction, the standard potential for this half reaction. If we look at zinc, zinc is oxidized in this reaction. So we can look zinc up on this reduction table, and you'll notice that zinc is down towards the bottom and it has a negative reduction potential. But if we flip the reaction for the oxidation potential, then we can flip that sign and we get zinc forming zinc 2 positive plus 2 electrons is a positive 0.6 volts. Anytime a reaction occurs, a redox reaction occurs, one substance has to be reduced and one has to be oxidized. And so in this case, the substance that really doesn't want to be reduced is the substance that will be oxidized. So we add these two voltages together, the one for the reduction, 0.34 volts, and the one for the oxidation, 0.76 volts, and we get the overall cell potential of 1.10 volts. So this reaction will produce 1.1 volts. So if you had something that needed to be powered by 1.1 volts, this cell would allow you to do that. Again, for a reaction to be spontaneous, the two voltages, the two electromotive forces have to add up to a positive number. Another way we could write the reaction occurring in a galvanic cell is what's called cell notation, where we take the two half reactions and we show how they're separated. So in this case, we have zinc and becoming zinc ions, and this is the oxidation reaction. So we put the zinc metal and a line saying that the zinc becomes zinc 2 positive. Then we put a double line. This represents the salt bridge between the two half reactions. The other half reactions is copper 2 positive becoming copper metal. And so again, we use a line to separate this reaction where the copper 2 positive becomes copper. And so the oxidation is always shown first, the reduction is always shown second. And this particular way of writing this is called a cell notation. It's just a simpler way of writing what's going on in a redox reaction or a galvanic cell. So let's write the cell notation and calculate the cell potential for this reaction. Iron chloride reacting with aluminum to produce iron metal and aluminum chloride. Now in this particular case, notice the iron chloride and aluminum chloride are aqueous. That means that the chloride ions are actually spectator ions. And so we can ignore those spectator ions and we see that aluminum becomes aluminum 3 positive. And so that is our oxidation reaction. And then we have iron positive, 2 positive ions becoming iron metal. And so that's our reduction half reaction. So our cell notation can be written like this for this reaction. Now we want to calculate the cell potential of the reaction, meaning we want to look at iron being reduced. So we can just look straight off this table, iron being reduced. Notice that is not spontaneous. Iron is not a spontaneous reaction for reduction. But also notice that aluminum's reduction is even less spontaneous. And so in this particular reaction, aluminum is oxidized, meaning we're going to flip that reaction. So first, let's look at the reduction reaction. Iron 2 positive, gaining 2 electrons to produce iron, is negative 0.44 volts. When we flip the aluminum reduction, we get the aluminum oxidation, and that is a positive 1.66. So notice that the substance that is oxidized has a more positive value than the substance being reduced with a negative value. So overall in this reaction, if we add up these two cell potentials, we end up with a positive value of 1.22 volts, meaning this reaction overall is spontaneous. So when we want to determine what substance is oxidized and what substance is reduced in a reaction, we simply look at which substance needs to be oxidized in order that the reduction and oxidized reactions added together will give us a positive voltage. So if we want to write the net ionic equation for this reaction, we can do that. what we're going to do is first determine which reaction needs to be flipped instead of reduced to give a positive E cell. Now, we did this in the last example, and so we've already seen that aluminum needs to be flipped in order to do this. So we know that aluminum is going to change and go in the other direction. Iron is going to be reduced, and we get a positive voltage of 1.21, which we saw in the previous example. That means that to write the balanced equation, we need to flip the aluminum, as we've done. And now we gotta just balance this redox equation, which we haven't done in a while. So let's look at it. Notice that the first reaction produces 3 electrons, but the second reaction only accepts 2 electrons. So we need to balance the charge of these 2 reactions by balancing the electrons. So we need 2 of the first half reactions and 3 of the second half reactions in order to balance the number of electrons. So I'm going to distribute that 2 through everything in the oxidation reaction, distribute the 3 and everything in the reduction half reaction, and add those 2 reactions together. And so you can see the overall reaction here, including the electrons. Next, we need to eliminate anything that's the same on the left and the right. And the only thing that's the same on the left or right is the electron. So I'm going to cancel the 6 electrons from the left and the right. And now I've got the balanced equation. 2 aluminums plus 3 iron ions produce 2 aluminum ions plus 3 iron atoms. And we want to check and just make sure this is balanced. So you'll notice I have 2 aluminums, 3 irons, and then we want to check for balanced charge. 3 times 2 gives me 6 positive, and 2 times 3 gives me 6 positive. So the charge also balanced. So this is the correct balanced half reaction. So that is a very quick introduction to galvanic cells. Hopefully that was helpful. When we talk about oxidizing versus reduction, the more easily something is reduced, the less easily it's oxidized, and vice versa. So, for example, the cell potential for the electric potential for the reduction of iron 2 positive is negative 0.45. But if we oxidize it, it's positive 0.45. So that substance is more easily oxidized than it is reduced. And as we look at this table, the most easily reduced substance was silver ions. The most difficult substance to reduce is magnesium ions. But the opposite is going to be true for oxidation. If we flip the signs and flip everything else, we'll see that it is more easily oxidized as you go down the table as opposed to less easily reduced. So oxidation and reduction are always going to be opposite of one another. So that's it for an introduction to galvanic cells. I hope that was helpful. If you have